In your chemistry book, chapter 7, light, electrons, and atomic structure. So you see what we're going to talk about is light and how light's related to electrons and the structure of atoms. When you think of light, what do you think of? Well, I think of the Lord Jesus Christ because he said that he is the light of the world and how light enlightens or so that we can see through any darkness that we have. And the Bible also says that we are a light because we have Jesus in us and not to hide our light. I love all that when we're discussing light because in actuality, science only knows a little bit about light. There's a lot of things about light that we don't know. It's very uncertain, and we're going to find out about that, the uncertainty and the quantum mechanics of light, and get into some of that. So let's begin to study this magnificent subject of light. Here you have a picture right here, how magnificent light is in the colors that we can see. Here's some key symbols, and we're going to go over this symbol, which looks like, it's a Greek letter, looks like an H, but it's not. It means wavelength. It's a lambda Greek letter. Frequency, making frequency. Hertz. Hertz means basically how you measure frequency of waves. And C would be the speed of light. And this sign is gamma rays. And then we're going to go into Planck's. We're going to go into this in the next video. So these are key abbreviations that you need to know in the midst of this. And going on, we're going to talk about the nature of light. So first, the light, as I said before, has to do with the arrangement of electrons. But in the beginning, well, when they discovered the atom, they tried to find out what these electrons were about, right? And so they wanted to determine chemical properties of elements, and they find the electrons had to do a lot with the chemical properties of different elements. And in basically, back when you go into the 16 and 1700s, they knew little about this, right? So first of all, they had to find that electrons existed as the first state. And later on, the decades would pass with a lot of brilliant scientists trying to find out characteristics of light. So what is the nature of light? The light of the world? Yes, but we know that light is from energy. And the study of light is a breakthrough. So they tried to study electrons and all that they could, all these scientists, but not until they started studying light did they find out more about electrons and photons, which are packets of electrons. So it's pretty spectacular to know that light is something that's, when I think of it, I think of it almost as in supernatural in a lot of ways. So let's talk about light, and we're going to talk about properties of waves, because they have found out that, and we'll show the history of this, that the properties of waves can be related also to light. We know what waves can be related to anything going through a medium, like, a wave going through the water or sound going through the air. But with light, we don't have a medium to go through. Basically, the waves are just going through empty space. So it's a lot different. But before we can really look into light, let's look at some of these properties of waves. This should be a review for you. So the properties of waves. Waves, of course, are that periodic back and forth movement that you see. If you're laying on the beach and you hear the waves, they can come in. Here they come, very, very smoothly in, and, just relaxing you. You can relax with the waves, or they can have a lot of energy and come in like a hurricane. So we know that waves and this periodic back and forth have certain characteristics. And so they have elevations and they have depressions. And so let's look at this picture. As you see this wave, this is the movement of the wave, and it's going this way, right? As it says, as she shakes this string here, or this cord. And so we have a wave. Well, we know that the top of the wave is called the crest, and the bottom of the wave is called a trough. And that's pretty important to know in measuring, right? And then, of course, we have the wavelength. And the wavelength would be between one crest and another crest, or one trough and another trough, so that we can basically see how big that wavelength is. Another property would be amplitude. And you notice this as amplitude as you go through here. It's the height. But the thing is, there's going to be a line of halfway point there. So the amplitude is going to be 1/2 the height. Because if you take the height of a wave right here, it would be this plus this. It'd be 2 times 2 amplitudes. So when you measure amplitude, it's going to be 1/2 through as if you put a line directly in the middle. So amplitude. So again, wavelength, the distance between two corresponding troughs or crests, and amplitude now is going to be the height of the wave and equal to 1/2 the vertical distance between a crest and a trough. 1/2. Just remember 1/2. Frequency now. What is frequency? Well, let's go on to the next page. Probably would show frequency a little bit better. So let me go to the next page. So amplitude here of a wave can be considered a measure of wave strength too. So the amplitude of the wave, how big the wave is, has to do with its strength. The amplitude of a water wave has to do with the wave's height and is equal to 1/2 the vertical distance, which we already said. So that's that amplitude. So the amplitude also has to do with strength. And when you're measuring wavelength, you're going to go by these lambda. See this little lambda sign? That's the sign that right here looks like a little h, and that means wavelength. Well, now let's talk about frequency. Because remember I said so far we have wavelength, amplitude, and now we have frequency. Frequency is the number of complete waves that pass by a certain point in a given time. Frequency is if you're timing the waves and counting the waves as they go through. So then you can, as you count the waves that go through, you can see how many are going through per second. So the SI unit would be hertz. Hertz is right here. Hertz is that SI unit. The SI unit is the international unit to measure waves. Is going to be in hertz. And 1 hertz, 1 unit, is 1 wave per second. So 1 wave per second would be a hertz. And that would be the frequency. But then, of course, we have something else. We have speed. Speed here. Okay, what's the speed? Well, the speed of the waves is the rate at which a wave travels. It's how fast it travels. It's velocity. Velocity is speed, only in one direction. And then you have the wavelength and the frequency. The reason we need to know about the speed and how to find the speed, we actually have a formula for that. So we have this formula. See, V equals wavelength times frequency. Very important formula, because if in that formula, you could actually find out, if you have a wave and you have the speed, you could find out the frequency. Or if you have the frequency and you have the speed, you could find the wavelength, So this is really important and an easy equation, really. So basically, when you have the speed, you'll know if you increase the frequency, here's the F, if you increase the frequency, you are going to decrease the wavelength. So a frequency would be a wave that's going back and forth very, very fast, like I was going back and forth very fast, very fast. It would be very short wavelengths, right? But if it was a very long wavelength, it's going back slow, be big waves. And that way, the frequency you count by is going to be a lot less. So you can see how that equation works, with volume and frequency. And I'm going to go over these right at the end real quick too, so you'll have them, you can write them down. So let's start. We're going to go classical theories of light. And that's going to be in here. And first we start here as light as a particle. So when we think of light as a particle, so we're going to talk about these guys, some of these guys that are scientists, and we're going to go all the way back to the 1600s. In 1600s to 1700s, we find, of course, famous scientist Sir Isaac Newton, a Christian too. And Sir Isaac Newton wrote a book in 1704, actually, called Published Optics. He loved to study light and colors and properties of them. And so his whole theory was that called the particle theory of light. And that theory was the idea that light can be pictured as streams of tiny particles emitted by light sources. So what Sir Isaac Newton thought? He thought that light were made of little particles. So we called that the particle theory of light. So everyone thought, yay! And of course, Isaac Newton was very famous. So everybody thought, we're going to believe exactly what he says. But at the same time, we had another scientist, and he wasn't known so well, and you probably don't know his name so well, but his name was Christian Huygens, right here, Christian Huygens. And he lived the same time as Isaac Newton. But he proposed another theory, and he said basically that light is a wave, which states that light consists of a series of waves, and it wasn't individual particles. And so in the midst of Christian Huygens, I should say, Huygens, basically him starting this, people started looking into later on, actually a century later, that maybe light is like a wave. So here we have another scientist you need to know. We have James Clerk Maxwell, very famous scientist, 1831 to 1879 is when he lived. This is like in the 1800s. Remember, we were in the 1700s. It's at least 100 years later. And he was a Scottish guy. He was Scottish, and he said light waves were described because of the electrical field. But not only would the light waves have an electrical field, but they had a magnetic field. And these two fields, they actually were at right angles to each other. They were perpendicular to each other. And this was really foundational. See if I can show you the picture. Right here's a picture, this picture here. So you can see here, we're going to have we have waves coming this direction. See how the waves are going this direction with electrical waves, and we have magnetic fields going this way. See how they're perpendicular? They're two different waves perpendicular to each other. And they thought this is electromagnetic wave. And just remember, electromagnetic, perpendicular to each other. And these waves behave a lot like sound, a lot like water waves, but they don't require a medium to go through. That means they don't require water, they don't require air to go through them, they just are going through in space. And that was the difference. Electromagnetic waves travel through this empty space, and they travel at a certain speed. And he figured out that speed, which is very important now. It's I know it is 186,000 miles per second. Or you can know it as a scientific figure, and here's the number down here, is 3.001 times 10 to the 8th power, or 186,000 in a vacuum. So it has to be in a vacuum, but that's how the speed of light is, 186,000 miles per second, or 3.3 times 10 to the 8th power, and that would be basically going into meters per second. I said miles, but this is meters per second. So that would be your SI. That's what they would go by, because a lot of people don't go by, in other countries, go by miles necessarily, but I always know it as 186,000 miles per second. So you need to know that. The measure of the speed of light in a vacuum never varies. And it's always, basically the value is always the same. And so there'd always be a constant. So the measure of speed in light and vacuum never varies, it says here. Let's go on to the next. No matter what the circumstances are under, it's going to be the same. Well, I have to say, it's kind of weird now, but in these last few years, they've thought that maybe the speed of light is slowing down a little bit. That is kind of a different theory, because it would freak scientists out. But maybe the Lord's going to come back soon. I don't know. Is that a sign of the times? But anyway, that's not in your book. But it is true. You can look it up. So anyway, as with sound waves, we have the frequency, wavelength, and speed, and they are related. Basically, the speed of light is c. It's going to be there. It's constant, 186,000 miles per second, and it's going to equal the wavelength times the frequency. So you need to know that little formula, similar to the other wave formula there. So, and this is the speed of light. Just remember this, c is the speed of light. Okay, and this will say basically the same thing. If the frequency is really high frequency, it's going to be very short little waves. And if it's a really high, big, long wavelength, then it's going to be, the frequency is going to be really slow. So same as it would be with any other type of waves, whether they be sound waves or waves in the ocean. But the range of electromagnetic waves is from 20 hertz, that's very slow. That means 20 hertz, you know, through each 1 second, going through a second, the hertz does, the hertz sign does, to over 100 trillion megahertz, the frequency. So it can go from like 20 hertz to 100 trillion hertz for electromagnetic waves. That's a huge amount, isn't it? So the wavelengths of low frequency electromagnetic radiation may be measured in thousands of meters, while the wavelengths of high frequency radiation are measured in nanometers. That means 10 to the -9th power. That's how those wavelengths are very small, and they're very, very fast. So let's talk about the electromagnetic spectrum here. So here we go. This is what I want to do. So here we have an electromagnetic spectrum, and you probably have seen this before. So Maxwell, now we were talking about James Clerk Maxwell finding these electromagnetic waves. Well, Maxwell predicted that electromagnetic waves can exist at lower and higher frequencies than visible light. And he wasn't sure about that, but later on, sure enough, there were waves. So here we have this visible light is just tiny on our whole spectrum of electromagnetic waves. We have visible light coming out here, and dividing that in, you can see the different frequencies and wavelengths of this light. So later we found radio and x-rays and all these, and so now we have all of these waves that you can see, and some of them on here, and you can see the wavelength and the frequency of the waves. So light here we're looking at different, we'll have the fastest frequency up here. See how these are going? These are gamma rays. And then we have x-rays. They're really fast too for x-rays. We discovered those not too long ago. And then right above, you know, a little faster than visible light, we have ultraviolet light, you know, and the ultraviolet light, remember, but all of these ultraviolet x-rays and gamma, they could burn you. So ultraviolet light. And you think violet would be, so we look up here, violet's on the sides of the greater frequency than red. So you need to know these colors too, and that'll be kind of a test question. And then of course we have the infrared rays, and they go to a lower frequency and on to microwaves and radio waves and electric power waves all the way through here. So 1, 2, 3, 4, 5, 6, 7. So if you go through all of these, you'll see, and you can see where you could have use these for x-rays and PET imaging, onto ultraviolet rays here. Here's where they have radar, cell phones, radio waves, all in the lower of frequency. These are increasing wavelengths. They get bigger wavelengths as they go this direction, and they get higher frequencies, which causes more energy. This is the electromagnetic spectrum. Okay, let's go on to the next. Let's go back. We're going to start right here, and we're going to talk about the quantum theory of light. In the 19th century, there were two scientists, and these scientists are very well known, and they found a paradox with light, and it was definitely a breakthrough. that basically some characteristics of light can be explained only if light consists of waves, yet other characteristics can be explained only if light consists of particles. They're like, what is this light? Is it a particle or is it a wave? And so now's the thought on this. And of course, we have a lot of scientists during this time thinking about it. Finally, there were these two scientists I talked about, and one of the scientists was named Max Planck, very famous, and these are basically in 1900, and Albert Einstein, which you probably know about Einstein, in 1905, showed that light can be classified as particles, but not simply as particles or waves, but light has characteristics of particles and waves, but doesn't take on the particles sometimes and doesn't take on the waves sometimes. So certain aspects of light, especially those dealing with how it is transmitted, are very wave-like, they look like waves. But other aspects, especially those dealing with how it interacts with matter, are very much like particles or bullets. So this two-sided nature was known as the wave-particle duality. And so this is Einstein, this is Planck. Now they're talking about something entirely new. We can't consider them totally particles. We can't consider these light totally particles, and we can't consider light totally waves. So what do we consider them? So as they started describing electromagnetic radiation, they would come in small packets. They said, it seems as it's transferred in little groups or bundles of energy. And they called these little bundles of energy quanta. Pretty important, quanta, that word. You probably hear it now. Quanta actually means how much. And so they developed what was called the quantum theory of light. And it states that light consists of tiny bundles or packets of energy. And these little tiny packets of energy are called photons. So photons, guess, are packets of energy, packets of electrons. So now we know electrons, photons, packets, quanta, all similar, all the same. Quantum theory of light is so important with these packets. The amount of energy the photon contains is proportional to its frequency. So if the frequency is faster, a faster frequency, of course, there's going to be more energy in a photon. And photons interact with matter, and they act like particles. Photons will act like particles when they're traveling through space. Sometimes they seem like they're particles. But then again, that when you take light in the electromagnetic scale and everything, and as they're traveling more, they'll act like waves. So I would say, actually, when they're traveling, they act more like waves. And then particles, when you take each particle, you'll find how that particle can hit another atom, and that atom letting out more photons. So it turns like, are they individual or are they in a group? And now we don't totally know, but we think they are both. So light are electromagnetic waves traveling as photons. Remember the word photon, very important. And light must consist of whole numbers. You can't have a half of one. So you can't say, oh, there's a half a photon, or a photon is a group of them, but as they're traveling, they're traveling by numbers, and you have to use whole numbers, is what it's saying there. And going on, the energy E, that's your energy, is directly proportional to the frequency. So here's what we have now. So here we go. The consequence of quantum theory is that light must consist of whole numbers of photons. A photon can't exist. Just like when you go to a local fast food restaurant, you may order 1 hot dog, 2 hot dogs, or N hot dogs. You cannot purchase 1.28 hot dog or 3.42 hot dog. Of course not. They must be ordered in the whole numbers. And so according to this quantum theory, the energy of a photon is directly proportional to its frequency. Here's the frequency. And so the H is Planck's constant. He had to figure that out. So we're not going to figure that out, but his constant is 6.63 times 10 to the negative 34 joules per second. This is, very, very small. We're talking very, very small. I mean, very, when you think of very small, you're thinking how how small electrons really are. Since only whole protons can exist, the total energy of monochromatic single frequency light must be a whole number in the multiple of HF. So he figured this out. We're not going to figure that out. That'd be very, very complicated right now. So E equals HF of a photon. So how important is that? So let's go on, and I'm just going to go over some of these questions, which are not that hard, and this will be the end of this video. Well, first of all, let's sketch a wave and label the amplitude, wavelength, and frequency and define these terms in your own words. So we already did that back when, or showed that picture back when. Let me show it and you can do that. Let's see. Sorry. It's really going slow now. Let's go back. Basically what you're going to do is you're going to show a wavelength and you're going to sketch it with the amplitude being its height of the wave, 1/2 the height between a crest and a trough, and the wavelength being between one crest and then one trough, and then the frequency is going to be how many of these waves pass by a certain point in a certain point of time. And hertz being how many waves, one wave passing through in 1 second. And so what is a photon? Electron little packet, right? Tiny packets of energy, of light. Photon is always concerned with light. So that's pretty easy. And now it says refer and arrange the photons of green, ultraviolet, red, and blue light in the following order. Well, let's go back to that. Hopefully we'll go back there, see if it'll go up. There we did. So here we're gonna go. We're gonna look right here. So if we were gonna arrange these, first of all, increasing wavelength. So we're going to look at the wavelength. Here's a big wavelength, and these are tiny wavelengths. So if we looked at these colors, violet would have the smallest wavelength, right? It's not going to be very long. From one crest to another crest, it's going to get smaller. So violet would be the smallest. So if we want to put them from smallest to largest, we put violet, blue, green, yellow, orange, red, just the way they want. From the smallest wavelength would be here on, and the red would be the biggest wavelength. Now we want to put them together by frequency. We want to put a frequency. That means frequency is how many times they're going, how fast they're going. That would be the frequency of how many go through a certain period of time. And so if the frequency, for increasing frequency, what would it be? Well, increasing frequency, we'll see the red has less frequency. That means it's not going up. So it'd be, if we were doing it for increasing frequency, it'd be red, orange, yellow, green, blue, and violet, because violet would be very frequent, had a high frequency. And on to the increasing energy. Increasing energy has to do with frequency. The more frequency, the more energetic, right? So the same would be for increasing frequency, we're going to be going this direction. Here it says increasing energy is this direction. So we'll be going red, orange, yellow, green, blue, and violet for increasing energy. Increasing frequency and energy are the same. So let's see, gamma rays and radio waves, as you see here. What's gamma rays on here? Gamma rays are up here to 10 to the negative. This is gamma rays, 2 times 10 to the negative 7th. Well, it's clear up here with gamma rays, and we'll see radio waves are way down here. So let's go back to that question, see what that question was. I didn't. Some gamma rays originate in deep space, have wavelengths on the order of 1 times 10 to the negative 18th meter, whereas an average radio wave had the length on the order of 500 meters. You see, huge difference. The energy associated with each of these radiations is as follows, okay? So you have gamma waves are going to be 2 times 10 to the negative 7 joules, and radio waves are 4 times 10 to the negative 28 joules. So the difference. By what factor are these gamma waves more energetic than the average radio waves? By their frequency. Remember, frequency has to do with how fast, frequency has to do with how much energy the wave has. So gamma waves are going to have a lot more energy than radio waves. So, well, let's stop there. I hope you're kind of understanding light. It's kind of neat, but you can get these formulas in your mind and all these things, but very much this subject of light is ongoing and changing even in the times that we live. And I think that is so amazing because Jesus said he is the light of the world.